We covered radar. We've covered, y'all remember the Doppler? You probably get a question on Doppler, just being honest with you on the test. You're probably going to get a question about radar, almost guaranteed, and probably an equation about freeze. But I can wrap those three into one problem statement with an antenna on an aircraft. So just remember that. The next thing I'm going to just say before I'll answer questions. I'm trying to give people a chance to get here. The next thing I'll say is we have done arrays, and it was with that, the magnifying effect of an array, a linear array with a constant phase, it's where psi is equal to 0 is where the maximum will be. So for the magnifying effect of the array, it's the magnitude of sine of n psi over 2 divided by the sine of psi over 2 quantity squared. But it's the magnitude that is going to be actually the magnifying effect on whatever the element is doing. And psi is beta d cosine phi or cosine phi plus the phase angle alpha. Talked about individual antennas. I'm going through and just revamping stuff we've talked about so it'll be in your head. And we're going to address some things. When we had that, we had a half-wave dipole and the equation for that, for gain, and for the electric field. And we had a arbitrarily long dipole, straight wire dipole. We had a loop, a small loop antenna. We had a short dipole. Those were the specific antennas we talked about. We defined where the far field point was, which happened to be, do you remember for a straight wire antenna? Lambda over 2 pi, right? If you're further away than lambda over 2 pi, for a straight wire antenna, you're in the far field. Okay. Then we talked about plotting the power pattern, determining the total radiated power, getting the gain if we had a normalized power density. Did you all remember that? These are things you'll be responsible for. Everything I mentioned, responsible for, and they're all reflected in the problems I assigned. We also, if we keep going back, we talked about waveguides. We talked about waveguides and the operating frequencies and how to determine them. Rectangular. I'm not going to give you a question about fiber optics. For a rectangular waveguide to operate correctly, in general, you should be between the 1.0 and the 2.0 cutoff frequencies. And we talked about using a waveguide like we would a transmission line to communicate power or information from over a finite length to a given antenna. All right, that was sort of waveguides in a nutshell. Then we talked about the electric field and the H field in the far field. And what happens when you have a lossy conductor, I mean basically a good conductor, or a low loss dielectric, or if you're in free space, right? And how to go about determining that. We also talked about phasor domain, and we talked about the continuous time domain for propagating waves and how to go from either phasor to time or time to phasor and vice versa. We talked about power flow being equal to 1/2 the magnitude of E squared over the magnitude of eta times the cosine of the angle associated with eta times e to the minus 2 alpha z would be an actual power average power density if it's a plane wave propagating the z direction. Talked about how to calculate alpha and beta equal to gamma, which is the square root of j omega mu times the quantity sigma plus j omega epsilon. Now I'm stating all these things that I'm just trying to trigger your mind to think about the concept. We talked about reflections, normal incidence, and oblique incidence. A good question is, would you be responsible for oblique incidence? Remember, there are TE and TM modes, right? What mode allows for nothing to be reflected if you have dissimilar media? It is the TM mode, right? And there's a thing called the Brewster angle. And it's also, right, this is for a propagating wave. It's not in the waveguide TM mode. I'm talking about in a propagating wave, there is a certain angle called the Brewster angle that gives you total transmission. Nothing is reflected. It's an interesting concept because you have media with different values of eta, yet nothing is reflected. It's counterintuitive. If it was normally incident, you wouldn't get reflection. But that works. Then, what else do we talk about? Polarization, circular, elliptical, or linear. And that's sort of in a nutshell all the concepts. Did anybody remember what I said about arrays? Didn't I say the sine n psi over 2 divided by sine of psi over 2 squared? When you're talking about the effects of the array itself, if you have an array and say you have n elements, and it goes from 1 to n. Now we don't care what kind of elements. If you have this, there's a thing called the array factor, and I'm not talking about the power here. This is, and I'll even put down, this is the magnifier on the E field. And that's going to be simply the sine of n psi over 2 over the sine of psi over 2, where psi is equal to beta d cosine of phi plus alpha. Now alpha is going to be the progressive phase shift. So this would be 0, here is alpha, 2 alpha, 3 alpha, and so forth for the phase shift on current. This is the magnifying effect on the electric field. For instance, if you had a short dipole here, and by the way, this angle phi is measured the axis of the array. This is a real important concept. Always measured from the axis the array is on to that point, the radial vector r, where you want the electric field. However, we know if we have a dipole oriented this way, the actual electric fields of the dipole, say it's a short dipole, and this is theta, I know the total electric field here, it will be in the direction obtained by the element. Here it would be in the theta direction because the element's in the z-axis. So here we would have j eta beta, and then would be times I naught times L. That would be the current magnitude on each element over 4 pi r e to the minus j beta r. Then there would be a sine of theta, and it would be in the a theta direction. Y'all with me, class? That's the element. Now, if you want the actual electric field and you had an array of these things, then you're in the far field. Then you have to multiply it by this. So now it would be multiplied by, I'll just call it the array factor. And the array factor, that angle phi right there, is not theta. It would be what? 90 degrees minus theta. And depending on what alpha is, it controls the phase shift. Now, this is for the electric field magnifying, the magnifying power of that. When we talk about power density, P ab, and for the same exact thing, the average power density at this point, here, the average power density would be the average power density at that point of the element. Y'all with me? So for a short dipole, it's 1/2 the magnitude of E squared over eta naught, right? And the magnitude of E squared is going to have a sine squared theta in it. Y'all follow me? It's going to be times the actual magnitude of the array factor squared. In Dr. Wentworth's book, he calls it F. Now you just take the magnitude of this and square it. I'm going to say this. If I give you anything resultant that's an array type of effect, I will give you this. I'm not going to expect you to memorize that in this. You just saw it. All right? I'll give you that. I don't plan on giving you anything that should be a struggle. It's based on the homework. Some of you were in my 3800 class. All the problems you got were just homework problems, modified. Slight modifications. It was a trivial test, and I'm sure I'm sure the score is going to be very good. I know one person at least did very good. Probably a lot, because it was the simplest test that you can get. The EMAG test is basically going to be the same. I mean, if you look at the homework and you think about the test, there's simple modifications. There's no tricks. It will be the same here. But I warn you about one thing. Don't cut yourself short by saying, oh, I kind of understand this, I'll just move on. That's where you get killed. I promise you, you'll fail this course if you do that. And in the summer, the bad thing is so many people, and I don't know where to start it, they go in and they have an expectation, well, if I take a summer class, I know I'm going to pass. And then they fail and they don't know what happened. I'm trying to make sure it doesn't happen. Please don't take this lightly. Study hard and study frequently, and don't cram and get your sleep. I'm doing everything I can to help you, but I don't know what else to do. How about open it up for questions?
Did you read, kind of explain what you meant by what might get asked for oblique incidence?
Oblique?
Yeah, you mentioned something about a certain TM.
All right, I would give you the equations for reflection and transmission coefficient for TE and TM. So if you have an oblique incidence, I'll give you an example. Now, I would provide the equations. I'm not expecting you to memorize those. Let's call this boundary, this material 1 and this material 2. All right. And I'm going to have a propagating wave. I'm going to draw this as, call this the z-axis and call this the x-axis. So if I have a wave, but if I have an electromagnetic field, now here's the thing. It's going to be propagating in this direction. The angle is always measured with respect to the normal for the equations in Dr. Wentworth's book, and in general. That's the incident angle. Actually, I'm glad we asked this because I didn't mention Snell's law, but you're going to need Snell's. This is, this is eta 1, eta 2, but let's say it has epsilon relative 1 and mu relative 1, epsilon relative 2, and mu relative 2. You all with me? And we're going to let's assume losses. Now, the electric field can have two component directions in general. It could be a superposition of them. One would be something called the TE mode. That's transverse electric. So if that dot right there, if the electric field incident is sticking out like this marker is, does everybody see that's transverse electric? It's called horizontal polarization. I mean, if that plane was the ground, you could see it's in the plane of the ground. It's parallel to the ground, horizontal. That's TE. If the electric field was like this, now the magnetic field would be out of the border, into the border. Actually, maybe what I should do is put it like this. Then the magnetic field would be sticking out, right? Be perpendicular. And this would be a TM, transverse magnetic polarization. You probably don't remember the relationship for the reflection coefficient, but you need to know Snell's law. Now, the way I always do Snell's law is beta 1 is going to be the actual value of beta in region 1 times the sine of the incident angle is equal to beta in region 2 times the sine of the transmitted angle. I said it was lossless. If it's lossless, it means beta in region 1 would be omega times square root of mu1 epsilon 1 times the sine of theta incident is equal to omega times square root of mu 2 epsilon 2 times sine of theta transmitted. Remember, this is the go-to if you can't remember anything, remember that. Now, I said it was lossless, right? We're going to start simplifying. You all see how omega goes away. Now, mu1 and mu2, epsilon 1 and epsilon 2 are based on the relative permeability or permittivity and the values of mu naught and epsilon naught. You all with me? Now, because epsilon naught and mu naught appear on both sides, get rid of them. This is really going to be just square root of mu relative in region 1, epsilon relative in region 1, times the sine of theta incident is equal to square root of mu relative 2 times epsilon relative 2, and times sine of theta transmitted. Now at this point I'm going to just say something. I gave you a problem on a quiz, and I was asked about this. John asked me, we know that eta in region 1 is equal to the square root of mu naught, mu relative 1, over epsilon naught, epsilon relative 1, right? By the same token, we could get eta in region 2. In either case, you know that eta in either region, I'll call it I, is going to be 120 pi because that's square root of mu naught over epsilon naught. You can pull that out in front, and then it's just the square root of mu relative I over epsilon relative I. So if you want the characteristic impedance in either region, you start with 120 pi, and you just multiply it by the square root of mu relative over epsilon relative for that region. Usually it's non-magnetic. I did give you a problem where it wasn't. Do you all remember that? Remember, this is eta. Now, what's the phase velocity? And again, we're talking about lossless region. Phase velocity, if it is lossless, is what? Technically, it's what? Omega over beta. Well, what is beta? It's omega times square root of mu epsilon, right? Omegas cancel here. And now what do you get? You get 1 over the square root of mu naught epsilon naught, which is c, the velocity of light. And then it's going to be what? Divided by the square root of mu relative over epsilon relative. Now, this time I'm going to point out something. If you're given the phase velocity, you have the product of mu relative epsilon relative given. If you have the ratio of E to H in any region, you have eta. Eta is also a function of mu relative and epsilon. So if an actual electric field is specified, you know the magnitude, and an H field is specified, you know the magnitude, you have eta. If you have eta, you have this. You have mu relative and epsilon relative for that region, ratio. If you have the phase velocity, you have mu relative epsilon. There's two equations, two knowns you can solve. What is the wavelength? Wavelength times beta is 2 pi, don't you? So wavelength would be 2 pi over beta. It's also C over F if it's lossless, right? I don't know if you remember that. But it's inversely proportional to frequency. Now all these things are important. Wavelength, phase velocity, intrinsic impedance, value of eta, the index of refraction, do you remember that? Index of refraction is nothing more than, technically, this is the index of refraction. I'm not going to give you the index of refraction. I'll give you information based on the most common stuff. Either phase velocity, value of eta, magnitude in E, magnitude of H. In other words, the usual suspects. So you can get either the incident angle or the reflection angle based on based on Snell's law, right? This is Snell's law. So let's say the wave is TE. If it's TE, and say I give you an electric field incident, and it's TE, and I say it's 10 e to the minus j, say 5x plus 2z, and call it in the AY direction. AY is out of the board. So I give you the E field, and call that would have to be region 1. Assume it's non-magnetic too, so let's say mu relative everywhere is 1. I give you that. So if I have that, I'm going to ask for this next. Direction of propagation. By the way, I would ask you this. I wouldn't say it's TE. What I'd say is, what type of polarization is that? It's one of two, either TE or TM. If AY is out of the board, if that's Z and this is X, Y is out of the board. If the electric field's out of the board, it is TE, right? Next, what's the direction of propagation? I would say if this is Z and this is X, I go up 5 units in the X, and I come over 2 units in Z, I'm going this way, and I draw this, and this would be my direction of propagation. If you look at this, if this is 5 up to this way, this has got to have a hypotenuse of 5 squared plus 2 squared, right? That means the unit vector in the direction of propagation would be 5ax plus 2az, and it would be over the magnitude of 5 squared plus 2 squared. Now the reason I know it's going that way is this minus sign, minus j. So it's going, these are the positive, that's the positive movement of the wave in that direction. Yeah. How do you find H? It's a propagating wave, right? Hint, it is a propagating wave. What are the cardinal laws?
Negative.
What? HI is 1 over eta, right? In the region, whatever region it is, and it's unit vector in the direction of propagation crossed into the E field. Now, what? Anybody else? What would be E if you had H?
Minus eta and AP
Exactly.
cross into H.
Now, E, it would be minus eta, and then it would be NP crossed into H, right? And the way you can always tell is E, if you want a sense of it, take the sense of the polarization of the E field, and then cross, right hand rule, cross it in to the direction of the H field. Your thumb points in the direction of propagation. That's how you get it.
Will we lose points if we don't show the full, say like we're getting an instantaneous form, and if we don't show phasor? And
If I ask for phase, you have to show. I usually, if I give you one form, I ask for the other, almost always.
Okay.
All right, just to make sure you know what you're doing. I could ask, how do you find beta in this one? Magnitude beta. Say in region 1.
Omega over.
Look here, how do I find beta if I know that? What do I know this form is that I have for the electric field?
How do you
If I
find
wanted
beta?
beta, just listen to me for 1 second. I know it's going to be magnitude of E naught. This is the general form. It's going to be E to the minus j here, and then there's going to be a beta here. That is the regional beta in that region, right? The magnet. Then it's going to be times x times the sine of theta incident plus z cosine of theta incident. Do you remember that form? How many do? Now look, I have beta times x sine theta would be what? 5. So beta, that is a constant, times sine theta, that's 5. Beta times cosine theta is 2, right? Now if you square both terms, you get beta squared sine squared theta incident plus beta squared cosine squared theta incident. Factor out the beta squared, you get beta squared times sine squared plus cosine squared, which is
1.
1, right? Take the square root, you get beta. You square both of those terms, 5 squared plus 2 squared, then take the square root, you got beta. Now if you have beta,
That was the magnitude of beta, right? that you're
that's all you,
Okay.
I mean, we
Oh,
didn't
yeah.
cover directional, the actual directional beta. I mean, there is something where you talk about, it's called a vector k, which is really the vector form of beta in our case. It's the vector wave number, and then, so beta times the sine of theta is beta x, or kx. Beta times cosine theta is going to be beta z. Y'all follow me? It is the wave number in either direction, but this is beyond what we care to cover in this class. You with me, class? Okay, anyway, so we have all that. I'm trying to show you this. So this is TE, and it would be in the AY direction. So I'm going to ask for first the angle of transmission. Can we get that angle, class? What was the law we always used to find? If we know angle of Snell's, that one. Yes, we can get it. Can't we, class? If you know incident, you can get transmitted. If you don't transmit it, you can get incident. Correct? Now, if I ask for the magnitude of the transmitted E field, now you need the transmission coefficient. Correct? The transmission coefficient is 1 plus the reflection coefficient if it's a TE mode. You're asking about oblique incidence, right? I'm trying to give you everything I can think of I could ask. All this is actually reasonable. So here, the reflection coefficient, I'm going to put the reflection coefficient for TE, and the transmission coefficient for TE is just 1 plus the reflection coefficient for TE. But that's not the case for TM, all right? And this is always going to have the form of, this is eta, it's not the index of refraction. It's going to be eta 2 cosine of theta incident minus eta 1 times cosine of theta transmitted over eta 2 cosine of theta incident plus eta 1 cosine of theta transmitted. Now you can calculate that if you have the incident and transmitted angle and you know what eta 1 and eta 2 are. If you have that and you want the transmitted electric field, you know it's going to be in the AY direction. Does everybody agree with that? So that would be one. Transmitted would be transmission coefficient, transmission coefficient is 1 plus reflection coefficient, so I just put down 1 plus the reflection coefficient for the TE mode. Then it would be times E naught incident. But here, you don't just write that down. It's different now, isn't it? Because now that beta has a different value. Y'all follow me? So now this is going to be E to the minus J beta in region 2, which is going to be different, right? Depends on the frequency. And then you're going to have what? X, but now it's going to be the sine of the transmitted angle plus Z times the cosine of the transmitted angle. And it would be in the AY direction. Here's the problem. Most people don't, they don't remember it's this times sine theta on the other side. Remember, we got beta in region 1 from here, right? We squared both of them and then took square root. We could get the angle of incidence from that too, right? If we just had that. We can get everything we want from it. Now over here, now we've got to calculate beta 2 first, and I'm going to show you something. Remember, beta in region 1 would be omega, and then it's times square root of mu naught, epsilon naught, right? Times square root of mu relative. Let's make it non-magnetic. So this is going to be mu relative equal 1 for everything. Square root of epsilon relative in region 1. That's beta in region 1. Beta in region 1, therefore, is omega over c times square root of epsilon relative 1. If I'm given beta in region 1 and I know omega, I can find out epsilon, or vice versa. No matter what's given, you can find out the thing that isn't given from that equation for beta. Now, what is beta in region 2? Well, it's still going to have an omega over c, right? And it's going to be times square root of epsilon relative 2. Now take a look at the ratio of these. If I divide beta 1 by beta 2, what do I get? Square root of epsilon relative 1 over the square root of epsilon relative 2, right? So if I have beta in either of these regions and I know epsilon, the relative epsilon, I can get beta in the other region. We had the transmitted angle, right? great question. And I want to know what this unit vector is in that direction of propagation. How do you get it? Well, this is 1, right, if it's a unit vector. This would be the AX component, right? This would be the AZ component, right? What do you know? Tangent of that angle is AX over AZ, correct? And this is going to be what? Square root of AX squared plus AZ squared. Of course, I will give you the equations for transmission and reflection, or I should say the reflection and the transmission coefficients for TE and TM if I'm going that route. And I'd probably give you something like this, because I think this right here, a lot of people won't remember. Shields are what? You got something, usually air, then you got a very thin area where you have a high conductivity, and you have air, typically, right? So you need to calculate the transmission coefficient 1, transmission coefficient 2, the actual value of gamma, and find alpha inside that shield. Typically, we assume the shield is thick enough that you don't have to worry about the multiple reflections. I would never give you a multiple reflection problem on an exam. It takes too long. Unless it was a final exam and I literally told everybody it's coming at you.
I do remember you mentioning something when we were going over it. You said like maybe on the test you have something where you ask for something like D over 2.
No, it's just the value of the electric field or power density at the middle of the shield.
Okay, and is that different than just like not the rating, but the average power density in the
Power density is power density if we're in the phase of domain. But the thing is, the power density is going down by what? E to the minus 2 alpha z. 2 alpha for power density. The electric field is just minus alpha. Power density is e to the minus 2 alpha z. Minus 2 alpha z if it's power. It's minus alpha z if it's electric field. I'm giving you an electric field incident, and it's going to be 5, and it's going to be e to the minus 2 times z times cosine of 500 t minus 30 AX. I may be violating the speed of light here, but first of all, what direction is it propagating in? AZ. What is its polarization? AX, right? It's in the X direction, correct? So now I want the phasor form of the electric field. What is the magnitude of the electric field? 5. Now what do I put next? Is right. You put the alpha term, right? E to the minus 2z if alpha is not 0. Right? After that, e to the what? Minus j 30z, right? And ax, right? What is gamma? Alpha plus j beta, it is 2 plus j 30, right? I know, let's assume mu relative is equal to 1. Now I know that gamma is equal to square root of j omega mu naught here, because I said it's mu relative is 1, times sigma plus j omega epsilon, right? Alright, so I know that gamma squared is equal to j omega mu naught times sigma, and then it's going to be minus omega squared mu epsilon naught epsilon relative. And what's that got to be equal to? 2 plus j 30 squared, correct? That's gamma squared. When you square this, what do you get? 4. And then if you look at this, when you square it, you're going to get minus 900 plus j 120. Just square this, right? 2 squared is 4. The last term, minus j 30 squared. Minus j is minus sign, right? Minus j squared. 30 squared is 900, so that's this term. Then you have to have 2 times this inner product. So I have 2 times 2 is 4 times 30, and that's going to be plus J120, right? Now, you can equate terms. You know 120 is equal to what? Well, that's the coefficient of J. That's equal to omega, right? Mu naught sigma. Then you know what? 4 minus 900 is going to be what? 896 minus 896 equal to what? Minus omega squared, right? That should actually be mu epsilon, and this is should be mu naught here. So it's going to be mu naught. You'll see where I'm going. Epsilon naught, and that's times epsilon relative. I just wrote that again. Do you all agree with this? If you look up here, one of the things you can see is mu naught epsilon naught is 1 over c squared. All right, so I can just put this over c squared. Now, if you look at this, the unknowns. Mu naught is 4 pi times 10 to the minus. I've got omega, and I have sigma, and I have epsilon relative unknown. If any one of those is given, you can get the other 2. Yeah, I could give you the phase velocity, so the ratio of omega over beta would be known, and then you could solve that. But that's just some of the things you have to consider if something like this is given. and I'm asking for epsilon relative or mu relative. If I said it's non-magnetic, chances are it will be, but don't bet the ranch on it. But if I did that, you could figure out the other factors if you knew that. This isn't really a trick, but it's something people don't see. Squaring that thing a lot of times saves a lot of trouble.
So like I can find the magnitudes pretty easily.
Of
but
what?
Then for like the E field, like the E field and the magnetic.
E and H field?
Yeah.
Okay.
Then converting them to the time domain is kind of tricky to me.
For oblique incidence?
Yeah, for TM.
Well, there you're not going to have. I mean, I don't think we covered that in class. But what are you going to have to do? You're going to have to say, if it's lossless, you're going to have. Let's say it's TE. Okay. You're going to have the transmitted field's magnitude, which would be transmission coefficient times incident field's magnitude.
Yeah.
Then it's going to be a cosine of omega t. Omega is going to be the same in either domain. Frequency never changes. Then it's going to be minus, well, whatever the value of beta was in that region. Remember how it had beta times the sine of the transmitted angle as the coefficient of x? So it's going to be minus that beta x times x minus that beta z times z. So you're going to have two coefficients, not one. D is 10 to the minus 6 meters. I'm going to call that z. I'm going to say z equals 0 here. I'm going to say everywhere mu relative is equal to 1, so it's non-magnetic everywhere. And I'm going to say I have a value of sigma 10 to the third, which is Siemens per meter. Say epsilon relative here is 1 as well. Of course, I'm going to have an incident electric field. I'm going to have an electric field in this region, anywhere in this region. I'll call it the shield, and I'm going to have a transmitted electric field. I'm going to say the transmitted electric field's magnitude, and call this air, and this air. Let's see, let's let the frequency be 2 gigahertz. Say the transmitted field is 0.2 volts per meter. These are, like, this is one that should be automatic. E over A, right? So it's going to be, and I'm just going to put this down. E transmitted over eta naught, because it's air, right? If it wasn't air, you'd have to put the value of eta in that region. Next thing is the incident electric field. Now here's what I recommend. Sometimes people aren't used to doing problems in reverse. They're looking for that all the time. So what you do is write the equations you know to get that. And you know, if I want the transmitted electric field's magnitude, what I'm going to do is take the transmission coefficient region 1. That's this. We'll talk about that in a second. Then, after that, I'm going to say it would decay is, I'm just looking at magnitude, e to the minus alpha in the shield times the thickness of the shield. That's how much it decays down, right? And then it hits the other side, and then I have to put transmission coefficient in region 2, right? And all this has to multiply E naught incident, right? In magnitude. Start with the magnitude of the electric field times transmission coefficient. That's how much gets in right here, just on the other side. Then it starts decaying at this rate, e to the minus alpha, right? It keeps going all the way down to D. Then you have to multiply by the transmission coefficient in region 2. Now this is normal incident. So what is the transmission coefficient in region 1? I can say it's 1 plus the reflection coefficient in region 1. Reflection coefficient from 1 to 2 would be what? Eta 2 minus eta 1 over eta 2 plus eta 1, correct, class? If you did that and added 1 to it, you get 2 times the impedance you're going into, right? Over, and that's the shield impedance, it'll be complex, over the shield impedance plus eta naught, because it's coming from air. Well, actually, you probably want to put magnitude on that too. Magnitude on that, because we're worried about magnitude. That's eta 1. What is eta 2? Well, it's 2 times the impedance you're going into, which is, right, eta naught. So it's 2 eta naught over eta shield plus eta naught. And how do you get alpha? Oh, yeah, I could give you a skin depth and ask you to give me alpha. Actually, that's brilliant. Thank you. So alpha is 1 over the skin depth, right? Just to be sure about that. I'm not going to use that because you get beat up. How to get an alpha, what do? Well, we actually say that gamma is equal to gamma here. Gamma is equal to the square root of j omega mu times sigma plus j omega epsilon in the shield. And if assuming sigma and epsilon and mu were known, and the frequency, you should just take the real part of that to get alpha. Do you agree with that, class? And then if you want skin depth, take 1 over that to get alpha, the skin depth.
And beta is just the imaginary part, right?
Right, and in a good conductor, beta and alpha are the same magnitude.
Right.
Okay, so you can get that, and you can get this. So we can get the incident electric field by dividing this by all that. Let's say I wanted the incident power density and incident. How do you get that? Well, 1/2 the magnitude of the incident E field, we assume we have it squared over eta naught, right? We just want magnitude.
Said alpha is the real part of that, right? Square
Well,
root.
That's gamma, right?
Mhm.
Gamma is the propagation constant, right?
Yeah.
So that's equal to alpha, which is the attenuation coefficient, plus j beta. Beta is the wavelength. Now I want this. I want the electric field at any value of z in here, not just half. Do I know the electric field right here? Class, just on the other side of this barrier. Isn't that the transmission coefficient 1 times the incident field? So in general, the electric field anywhere in this shield as a function of my value z in magnitude is just going to be equal to magnitude transmission coefficient 1 times E naught incident times e to the minus what? Alpha times z. That would be the magnitude. I give you a z, you give me an e. An idea that will come into your mind is, well, the power would just be whatever the power density is right there, times e to the minus 2 alpha z. That would be correct if you got the right power density. But this is in the shield. The power density, PM and as z, so this is in the shield, is equal to 1/2, and then it's going to be the magnitude of the transmission coefficient 1 times the incident field squared over the magnitude of eta of the shield. Then you're going to have to put down e to the minus 2 alpha z. You're good so far, right? But then you have to put down cosine of the angle associated with the shield. Now that usually is 45 degrees, which means the cosine here is usually 1 over square root of 2. This would be the power density.
Is the 45 degrees because of that it's a conductor?
Yes. What happens to eta if you have a good conductor? Now think about eta in general. Square root of j omega mu over sigma plus j omega epsilon. If it is a good conductor, what can we do? We can ignore that. Now you have a square root of j. Well, j is e to the j pi over 2, right? So really that means if it's a shield, a good conductor, then eta is some magnitude of eta, which is just going to be the square root of omega mu over sigma, but the angle here would be e to the j 45 degrees. With me? Or you can put angle 45. There's either polar or exponential form is fine. They mean the same thing.
Shouldn't there be an alpha down there?
2 alpha z. No, you're absolutely right, Bradley. I'm sorry. This is 2 alpha z. Sorry. It should be 2 times alpha times z. That's my bad.
I thought only the power was the 2 alpha z, and then E field was just 1 alpha z.
It is.
But that's E field.
You know what? It's supposed to be alpha z for E field. I'm so sorry. Electric field goes down as E to the minus alpha z, or alpha times whatever the variation is, z, x, y, whatever. And power e to the minus 2 alpha times direction.
So around how to calculate the P average at anywhere in the shield that is stands for.
Yes, that's what that is. That's at any point z. Z is measured from the beginning, just the entry point from the shield is 0. Can you see? Look here. Can you see that 0? Okay, that's where the shield begins. Here's where the shield ends. So when I say P av of z, it's anywhere, any distance you could put z is equal to the thickness d over 2. That could be d over 4, and that would be it. Reflection's where?
That one,
This one?
that one,
What's the reflection going to be there?
all of E plus ES.
It's
plus
what?
I.
It's the field incident on there, which is ES times, would be the magnitude of the field there is this without this tau 2.
The transmitted,
Yeah, without this transmission coefficient. That's the incident field. Then you'd have to multiply it by the reflection coefficient, which is going to be what? Eta naught, right? Minus eta shield over eta naught plus eta shield, right? It's going to be pretty close to 1. But that's a good question. Yeah, I could ask a problem. I'm going to ask you a shield problem now, guaranteed. All right, guys, I haven't made up the exam. So I'm surprised I didn't get hit by this one. How many problems? 4 or 5 pages, each with a separate problem statement. I'll ask questions related to multiple times. And if you look at the quizzes, that's the form each problem will have. There's nothing there's nothing coming at you haven't seen. And I'm not going to ask you to derive the wave equation or something crazy like that. Thank you for doing that.